Welcome back all of you. In the last class, we discussed about phase cycling. In the sense, we discussed lot about coherent order and how we can choose a particular coherent pathway. That is coherent pathway selection we understood, for which we discussed a lot about pulse phase and the receiver phase. Depending upon which pathway we are going to select, coherent pathway, accordingly we can get the receiver phase, provided we know what is our starting pulse phase. That was given by minus delta phi into delta p into phi, where delta p is the chosen pathway, which is P2 minus P1. And accordingly we found out for various examples how we could choose the particular coherent pathway. And we took the example of homonuclear case, and then we selected, for example, 3p minus 3p plus 2p, etc. And we found out how if I select a coherent pathway delta pi equal to minus 3, it selects only particular that one. And when, of course, for the when we found out for delta p is equal to 2, we also worked out what is the receiver phase, and then we found out the receiver phase, although it matches with that of the minus 3p, but then it was when you acquired the data, it was nullifying. So, the receiver phase which was chosen for minus 3p was rejecting that for 2p. So, we took several such examples also, and we discussed lot about how we can utilize the receiver phase. Also we discussed what happens if there are two pulses present, not only one pulse. If there are two pulses present, what can happen? Of course, you can define the pulse phase for and receiver phase for first pulse, let us say. We can work out whether it is delta p is equal to 1, 2, 3, minus 2, whatever we want. Similarly, we can work out what is the pulse phase for a second one, but then it is a combination. If I take, let us say, the first pulse, in the first pulse, let us say in the phase cycling, I will know what is the receiver phase. Keep that receiver phase, first, second, third, all the 4-step cycle or 8-step cycle what we choose. We have chosen an example of 4-step. Check the 4-step cycle. For each of these 4 steps, you keep the receiver phase of the second one constant. Let us say that is also 4-step. First is 0, 90, 180, 270 you consider. Here also 0, 90, 180, 270. For the receiver phase of this value, each go through one cycle and then keep the receiver phase of the second one constant. Then again vary these 4, now change it to the second pulse, receiver phase to be the second one. Like that you have to take the combination. So, if you have a 4-step cycle, 4 into 4, there are 16 step cycles will be there. And also we found out, we have worked out and saw when delta p is equal to minus 3, and we calculated what is delta p is equal to plus 1, and it was also selecting that. So, we also worked out a general formula for any phase cycling, any delta p which is coherent pathway what you select, depending upon the number of cycles you have for the phase cycling, 360 by n, n is the capital N if you consider. Then there is a general rule which we said minus delta p in plus n times capital N when is a multiple small number small n, where n is capital N is just steps of the phase cycle. We found out that is also possible, and that can repeat n number of times. There is a cycle of repetition of the phase cycle. So, this is what we understood everything, and some examples we took, and then this is a coherent pathway selection. Of course, when after we complete 2D introduction and analysis of 2D spectra everything, we took one or two simple example of using this selection of the coherent pathway for one or two simple 2D experiment, like maybe COSI 2D or DQF COSI, like that. And we see how we can utilize that, where we have a 2-pulse sequence, a 3-pulse sequence, how we can utilize this phase cycling, how we can select the coherent pathway. With that, today we will go further. What we have to discuss is the same thing we can do in a different way called pulse field gradient, PFG. We can utilize pulse field gradient and achieve or select particular coherent pathway what we want, like we did with phase cycling with using the pulses. One advantage here, in the case of the pulse sequence, if we consider using pathway selection by phase cycling using pulses, we have to have n number of repetitions, like 4 per steps. If there are 2 pulses, 4 into 4, 16 steps, like that. It is time consuming. On the other hand, by using what is called the pulse field gradient, you can do it faster. In a single experiment, if in a one experiment, one scan, you can choose the right pathway. That is possible. So we can see, we can discuss about pulse field gradient today and work out and see how we can choose the pathway. Of course, B naught is the highly homogeneous magnetic field that we know. External magnetic field what we use for detecting NMR signal is highly homogeneous. That is over a sample area. This is my sample. Over a sample area, my receiver RF coil is here. My entire RF coil area, this sample will be perfectly homogeneous. That means each nuclear spin experiences the same magnetic field. There is no difference in the magnetic field at all. And the homogeneity is so much, it is 1 part in 10 to the power of 10. That means in a 300 or a 500 or a 800 megahertz spectrometer, I must be able to distinguish any two frequencies that are separated by even 0.1 hertz or less than that. That is the amount of homogeneity resolution we get for which such a highly homogeneous magnetic field is required. So, B naught field is highly homogeneous. Now, can I make it inhomogeneous? Of course, you do not have to worry. Naturally, if there is inhomogeneity, we tune it, make it homogeneous by shim coils. That we discussed in the first course itself. If there is a time left at the end, I will tell you some experimental tidbit. We can discuss about data acquisition and processing once again for the benefit of those who did not attend that previous course. That I will come at the end. But right now I want to tell you, in addition to that, we can deliberately introduce inhomogeneity for the magnetic field in a controlled way. How do we do it? By putting additional magnetic field. This additional magnetic field is generated by a small coil which is kept in the probe, which is called a gradient coil. This additional field, magnetic field, you generate by passing the current into this coil. When you pass the current, it is a coil like this, it will be there. You pass the current here, it generates a magnetic field. And this, how do you control this magnetic field? I am going to tell you. We can do that. This additional field applied by the gradient is very small, and we can vary it linearly. It in fact designed to vary linearly along the z direction. We have a z coil, z gradient we can have. Of course, we have gradients coil for x, y, etc. But for our interest, we do not have to worry about x and y gradient. Z gradient we can select. The additional field applied by gradient coil, the magnetic field varies linearly in the z direction. Now, how do we design this coil is like this. We crude drawing I am writing. See, it is made to be uniform, it is 0 at the center. The field which is generated by this coil is made to be 0 at the center, and then it increases in the portion above, upper portion of this coil. From the center, if you go up, the field increases linearly. If you come down, the field decreases linearly. If you come down from the center of this coil. So, the gradient field that way, of course, it varies if you go up and down, but it is position dependent now. So, because as a spatially I can vary it. As you go from center towards to the top of the sample tube, or come down in the RF coil, in the gradient coil, the field keeps on increasing this way, here keeps on decreasing, the gradient field. So, that is another one point which we should know. The gradient field also leads to z rotation of the spins, because it is nothing but adding to the B naught field, because the additional field you are applying adds to this B naught field, static field. That means the precisional frequency in the entire sample varies linearly. I take the sample tube here, NMR tube, and I have a gradient coil here, and then in addition to B naught field, the field is varied here linearly. So, at every stage, at every point in the space, as you keep on going up, then what happens? The magnetic field keeps on changing. When the magnetic field keeps on changing, what is going to happen? B naught plus addition of the magnetic field because of the gradient, I call it, let us say, Bz or Bg. that will keep adding up. Here it keeps coming down. So, as a consequence, what happens? Different parts of the sample experiences different precisional frequency. So, that is another important thing. And here what happened? B naught plus addition delta addition magnetic field, because of the gradient is added up, here it is subtracted. As a consequence, what happened? Spins in the upper half of the sample rotates faster than the spins in the lower half. Please remember, I have the sample tube here, and this is the coil, and of course I have a gradient coil added here, and I take this one as the center. All the spins above the center rotates faster, and one which is below rotates slower. And what happens to the spins at the exactly center? If it is a considered on resonance, that means the gradient field is exactly at the B naught field, there is no variation, that will not precede at all. Spins at the center which is on resonance do not precede, but the spins in the upper half rotates faster and in the lower half rotates slower. This is the one which is diagrammatically shown here. Throughout the NMR tube, the magnetization appears as if it is appearing as a twisted coil. See, this is the center of the NMR tube at which it is 0. There is no change. Let us say the gradient field along z axis is 0 at this point. All the spins here are on resonance. It does not change at all. But once here, before application of the field, everything is actually having the same precisional frequency across the entire sample tube. Now I am going to apply GZ exactly matching with the 0 at the center of the tube. But this one, the spins are along with aligned at 0 will not precede because they are on resonance. But look at this, the spins which are above and below, they start rotating. One is faster here and slow here. And when you view from the top, from the top of the magnet, you feel top view is like this, as if it is rotating like this. For the entire tube of the sample, it is going like this. That means when you view it from the top, the magnetization appears to be completely dephased and no signal will be detected. That is important. Please remember, when I am seeing the signal from the top, the spiral is going like this. It is a helix, not spiral. Helix is going like this. And then we view from the top, it appears as if the spins are completely dephased. When there is complete dephasing is there in the xy plane, you will not get any signal, and that is what is going gradient does. It dephases the signal, and this inhomogeneity what you are going to create by gradient, you can control it, and by controlling the current in the coil. And what happens now? I take an example like this. The spins here are rotating faster, spins here are rotating faster when I apply the gradient current. Now here current is flowing in this direction, bottom of the from the center go to the bottom, current is put in the opposite direction. That is why I told you this moves faster, this moves slower, and it is all in the center is 0, and here it increases, here it decreases. Okay. Now what will happen if I reverse the current? Instead of applying current in this direction, if I reverse it, now what will happen? Remember, the z rotation can be completely reversed. The sample starts precessing in the other opposite way. In this sense, the spins which are moving faster here starts moving slower, and the spins which are moving slower here starts moving faster. In this sense, the precision of the spins here now becomes faster, precision of the spins here now become slower. So that is another important thing. Next question is, you may apply a gradient pulse in the gradient coil. Again, it is controlled by application of a pulse. What is the duration of this gradient? How long you have to apply? That can be given by a time t. We can control that. And if it is along z axis, sometimes we call it as duration time is z. We can also control that. So duration of the gradient can be completely controlled. Now you may ask me the question, what happens if I take the spectrum? It is generally you can get very usually in the static magnetic field being highly homogeneous, you will get a very sharp signal. But with the Larmor frequency getting changed all across the sample. When the different parts of the sample experiencing different magnetic field, the Larmor frequencies will differ. Then what we are going to get? We are going to get a broad hump because different samples are undergoing precision at different frequency, or otherwise spins are having precision with different phases. So what it means is the gradient introduces spatially different phases across the entire sample volume. Phase and frequency are related. Okay, that in the very first course when the beginning we have discussed. There it is nothing but phase and frequency, we can correlate them. The homogeneous magnetic field, this is what happens. I take an NMR tube, take the sample and put it, this is my RF coil area. Magnetic field is along this axis, Bz is 0 here, does not matter whether it is 0 or what, because the entire sample volume magnetic field is highly homogeneous, perfectly homogeneous. So what we are going to get? Homogeneous magnetic field with each sample, every nuclear spin which you are detecting for a particular nuclei, you experience the same magnetic field. As a consequence, you are going to get a single sharp peak. Of course, with the natural line width here, that also we know. So this is what we are going to do. We are going to get now. Now I am applying a gradient field along with the B naught field. Of course, B naught field still is homogeneous, but we are making it inhomogeneous by applying a gradient coil like this. Now what is going to happen if I apply gradient? We discussed what happened to the spins above 0 and below 0. Now there is Larmor frequency keeps on varying across the entire sample. As a consequence, you are going to get a broad signal. You can consider there are thin slices of the samples here, and each slice has actually what happened, the spins have different frequencies, but within the slice they have the same frequency, but from slice to slice the precisional frequencies are different. As a consequence, you are going to get unresolved number of precisional frequencies which are going to be a broad hump like this. Now you may ask me a question, what happens if the slice thickness becomes narrow? I increase the gradient, manipulate the gradient in such a way here that slice thickness I make it narrow and narrow, becomes very narrow. Then what happens? Then entire sample volume you can consider the continuous distribution of slices, in which case not only broad signal, you do not get any signal because there is a complete dephasing. That is what happens. So with the application of the gradient, the total B naught we can work out like this. Now B naught is the magnetic field. What is the magnetic field generated or total magnetic field now with the application of the gradient field Bg? Now Bg is equal to Gz because it is a gradient that is applied along z axis. G is the strength of the gradient. G is always given as the strength of the gradient. The subscript tells me that we are applying along z axis. Of course, what is B naught? We know it is a main magnetic field. And Gz, if I calculate Bg is equal to Gz, it is a spatially dependent part of the magnetic field. So we know B naught. B naught is of the order of several Tesla, 5 Tesla, 10 Tesla, 20 Tesla like that. But what is the gradient field? It is very small. It is Gauss per centimeter or Tesla per meter. Or in other words, if you take the Z in the centimeters, we can say over the approximately 50 Gauss per centimeter, 50 to 60 is the strength of the gradient field that we are applying. So gradient field is reasonably quite large. It may not be as large as B naught, but reasonably quite large to create complete broadening of the signal and completely make sure that there no signal will be detected when the slice separation becomes very small. So gradient field is approximately 50 to 60 Gauss per centimeter, which if you calculate, the line width turns out to be about 380 kilohertz per proton. 380 kilohertz. Remember, our spectral width is only about 10 ppm. In 500 megahertz, it is 5000 hertz, 5 kilohertz, but 380 kilohertz. That is the reason why when you apply a gradient, you will generally, inhomogeneity so much, in principle, there is a complete dephasing and you do not see any signal. Now, the same equation here Bg is equal to Bz equal to B naught, B naught plus Bg. Now, I am going to multiply this equation by minus gamma. Gamma is my gyromagnetic ratio. Why did I do that? Because I want to express this in frequency for some unit conversion. Do not worry, there is nothing much big magic we are doing. Simply we are multiplying this minus gamma to express in frequency. So, this become minus B gamma Bz minus gamma B naught and minus gamma Gz. This is the spatially dependent Larmor frequency. We calculated Larmor frequency just by multiplying by minus gamma. We know what is gamma, gamma B naught. It is a precisional frequency, Larmor frequency. You can express in omega, 2 pi nu or omega. This similarly, now Wz, I can call it as gamma Bz. So, if I put this as a gamma Bz as Wz, then what is my equation becomes? This becomes Wz equal to, this is omega naught minus gamma Gz. This is my equation now. This is spatially dependent frequency across the entire magnetic field, entire sample we are taking. This is what is, I did not do anything simply by multiply this equation by minus gamma and I know the Larmor frequency or precisional frequency is omega equal to minus gamma into B naught. You know that, do not have to get confused, nu is equal to gamma B naught over 2 pi. So, this 2 pi when it goes here, this can be called as omega naught, that is all is done, nothing else. Okay. And then this is the spatially dependent frequency across the field. The precisional frequency, precision to the gradient is minus gamma into Gz because of the gradient. Now, what I am going to do is, I let this G omega z, capital omega z as minus gamma into Gz. I am going to call it like that, just to make my mathematical writing very simpler. Then the spatially dependent phase I will define as phi of z across the sample z, across the direction z equal to omega z into t from the previous equation. Okay, so that is what the spatially dependent phase, which is equal to gamma z is equal to gamma into B naught into t. T is the duration for which you are going to apply the gradient. Okay. So, now we can define one thing for the coherence order, which we know. For the coherence order P, we can also find out what is the phase dependence along Z. Like we have the coherence order, we knew, we have worked out the coherence transfer pathway. For if I have a coherence order P, then this phase of this of that is dependent along the Z axis, that phase can be given by phi of Z is equal to coherent order P into gamma into Gz of t. Gz is we know, t is the duration, gamma and p is the coherent order. So, if for a particular coherent order I can find out what is the phase that is given by phi z. So, simply remember phi z equal to minus p into gamma into Gz into t. So, Z gradient phase depends upon various factors, that is what it means. The phase of the Z gradient depends upon various factors. First, it depends upon the coherent order P. It depends upon gamma of the nuclei, because different nuclei, if I want to have a heteronuclear pulse sequence, for it, if I want to select the coherent order for proton, coherent order for X nuclei, then accordingly you have to calculate differently because gammas will be different. And it also depends upon strength of the magnetic field, gradient field G, and stronger the gradient, faster the spins will evolve, and t is the duration of the sample. Okay. So, these are the things which important parameters on which the phase of the pulse, phase dependence of the particular coherent order P along Z can be defined. So, simply remember, if I have a coherence order P, the phase dependence of that along Z axis is given by phi of Z is equal to minus P into gamma into Gz of t. That is all, you have to remember that. Okay. So, the phase acquired by different coherent orders now are defined by various parameters. I can define by strength, I can define by duration, I can define by the gamma of the nucleus. These are the parameters which control the phase of the different coherent orders. Now, I will introduce something what is called dephasing and rephasing using pulse field gradients. We understood something about pulse field gradient. Already I told you about rotation and everything. Now, I consider the situation. I am going to apply 90-degree pulse, okay, on some nuclei, proton, let us consider. And before the 90-degree pulse, I am applying a gradient which is G1. Strength of the gradient is G1. The duration of the gradient is T1. For the time T1, I apply a G1 gradient just before the application of a 90-degree pulse. After the 90-degree pulse, I am going to apply another gradient pulse, another gradient G2. The gradient is G2, that is for the duration T2. You understand now what we are doing? Simply apply a 90-degree pulse. Before that 90-degree, we apply a gradient G1 for a duration T1, and immediately after the 90-degree pulse, we apply a gradient pulse for the duration T2 of strength G2. Okay. Now, G1 and G2 are the gradients and G1 T2 I told you already durations. Now, the coherent order before the pulse I call it as P1 here. This is P1 is the coherent order, and coherent order after the pulse is P2. This is what I am defining. If I want to find out what is my coherent order before the pulse, I call it P1, and after that I call it P2. This is how I define the coherent pathway. Now, just before the pulse, this is P1. Now, after 90 pulse, it is P2. Fine. Now, you may ask me what is the gradient doing there? What are the gradients doing there? Spatially dependent phase acquired, we can calculate. The spatially dependent phase acquired during G1, I already told you, the phase can be calculated by minus P into gamma into G into GZ into T, I told you. Now, for the coherent order P1, which is P1 gamma G1 ZT1, phase acquired during G1, because coherent before the pulse was P1. That coherence is now I call it P1. It is getting the phase, it acquires the phase which is P1 G gamma G1 ZT1. This is what the phase it is acquiring. Okay. Now, what happens to the phase immediately after the pulse? Now that now it is P2. Coherent order is P2. Same way you can calculate the phase acquired after the pulse by G2. Now, the coherent order is P2, gradient is G2 and duration is T2. That is all. It is simple two equations. Only what I did was I just varied the terminology here. If you remember, I did not do anything here. Only what I did was before I calculate the phase of the gradient, phase of the coherent order P1 because of the G1 gradient and P2 because of this one. So, I told you coherent orders phase can be calculated along z axis based on these equations. These two equations with I always remember. Now, I know what is the phase due to G1 and due to G2. But what is the total phase acquired during the both the gradients by the signal? When both the gradients are applied, signal will experience phases first because of G1 and secondly because of G2. Both the phases are there, and the total phase is sum. Sum is again phase due to P1 and phase acquired by P1 and phase acquired by P2 due to G1 and G2 for the duration T1 and T2 respectively. This is the total phase acquired. Now, such a large gradient, the signal will completely dephase and there is no signal to detect. Then what is the point in applying the gradient if we can't detect the signal? We must detect the signal, that is our aim. So, what to do? If the total phase somehow I make it 0, instead of total phase is something which is quite different with some of these two with a large gradient, then you do not see the signal. Instead, I will ensure whatever the phase it acquires during for the coherent order P1 during G1 and for the coherent order P2 during G2 does not matter. If I take the total phase, and make sure that the total phase becomes 0, then I can still detect the signal. That is an important condition. So, what we can do is, now I will put a condition, the total phase acquired, if I will equate it, then I am going to get the signal. I will detect the signal will not get nullified. So, now you do the simple arithmetic, then this will become like this. Now, gamma for the homonuclear get cancelled out, z is, you can cancel it out. So, what you are going to get, G1 by G2 is equal to minus P2 into T2 over P1 into T1. That is what you are going to get now. So, the phase of the signal are opposite in G1 and G2. Sorry. Okay. So, the phase of the signal now what we got are opposite in G1 and G2. If the G1 signal, in G1 if the signal moves in one direction, in G2 they move in the opposite direction, because that is what we saw here. They are opposite now. Okay. So, this is what it is. At the end, finally, what so happens, the total phase becomes 0. Now, we call this as rephasing. Okay. If the total phase is not 0, then what is going to happen? There is a complete dephasing, you do not get the signal. If I ensure the total phase acquired by phase coherent order P1 and P2 during G1 and G2, the total phase somehow equated to 0, then I can still get the signal. Then I say the dephase signal is rephased. This is the important point. And diagrammatically you can see like this. These are all uniformly, there is a perfect alignment here, and then the homogeneous thing. There is no change in the frequency. All the frequencies are same. Here frequencies, because of the GZ, they are all different. Different slices of the sample experiences different Larmor frequencies. They are all rotating at different precision frequencies. Okay. Now, the additional field introduced with the gradient varies along z axis. However, within each of the slices, they are all these spins are rotating and experience the same field. So, now what is going to happen, as the slice thickness becomes thinner and thinner, the gradient becomes stronger and stronger. In which case, when the slice thickness becomes very, very thin, eventually there is a complete cancellation of the magnetization over the entire sample volume. At the end of this gradient, the coherence over the entire sample volume is completely dephased and there is no observable signal. So, now what we are going to do is, we can reverse this one. So, now how do you reverse it, I am going to tell you now. Since the time is getting up, I am going to stop at this point. What I wanted to tell you is, in this class what I was trying to say is, I introduced the gradients. I told you how we generate gradients by a coil, and it is assumed to be at 0 at the center, and above, if you go upper half of the coil, then it is increasing and the spins are precessing faster, and below it is precessing slower, and the current is made to rotate in the go in the opposite direction below. It decreases, it increases. So, in fact, if you strictly analyze, the spins in the upper half goes in one direction, rotates in one, precession clockwise, spins below the gradient coil, below the center, presses in the anti-clockwise. Clockwise, anti-clockwise precision also will be there. I did not discuss more about this thing, because these are all two fundamentals conceptually, we can worry about it later. But what I wanted to tell you is, by applying the gradients before the pulse and after the pulse, we can make sure that signal can be completely dephased. If G1 is and G2 are the two gradients before and after the pulse, if the phase acquired is given by minus P into gamma into GZ into T. That is what I said. So, depending upon the coherence order, how much phase is going to be acquired, you take the total phase. The total phase turns out to be equal to 0, then you will get rephasing. You can still get back the signal. If the total phase acquired is not 0, it is a complete dephasing, you do not get the signal. So, how do we get the rephasing? What we can do, I will come back and tell you later. Thank you.